Hi everyone, so let's do this question. I'll set a timer for 20 minutes. Let's read the question. 96. Unique binary search trees. Given an integer n, return the number of structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. Okay. So if n is equal to, I'm given n is equal to 3, so I need to return the number of structurally unique binary search trees which has exactly n nodes. So n is equal to 3, it means it will have nodes 1 to 3, right? And I need to return binary search trees. What is binary search tree? Binary search tree means a binary tree where left is less and right is greater, right? Is known as a comparable key and satisfies. So this is 50 and left subtree will be less, right subtree will be greater, less, right subtree will be greater. Yeah, I know that, but what about equal? If it is equal, then can it be in both? Yeah, I guess so. If it is equal, then will it be left or right subtree? So there are no any equal values in binary search tree then? Smaller than parent node, greater than parent node. What if it is equal? I don't know. Lower value and higher child has a higher value. Right child has a higher value. What about equal? I don't know. It's okay then. Maybe in binary search tree they will know. Yeah, but here there will not be any equal in this question because n is equal to 3 means there will not be 1 to 2. It is always 1 to 3. So it's okay. I don't need to know that. Structurally unique binary search tree. So how will I return it? Which has exactly n nodes of unique values from 1 to n. How will I know how many? How will I know how many structural unique binary search trees are there? 1 to 3, 1 to 3, 1 to 3. This is an interesting question. How will I know that? I'm thinking. So if it is 3, 1, 1 to 3, then it will be. It can start from 2, I guess. And then 1, 3. Right, and another one can be. The greater number should always be on the top. Smaller number can never be on the top because. Or it can be actually. If it is 1, then since all the numbers should be on the left side, right? So 2, 3. And if it is 3, then it should be left side only, everything. 2 and 1. And what else? I'm feeling very sleepy today. That is why I've turned off my video because I'm very sleepy, and it's 9 p.m. but I'm sleepy because yesterday I slept really late beyond my bedtime. Like, I know usually sleep at 11 or 10, but yesterday I slept at like 2 or 3. So today I'm feeling very sleepy this early. Anyway, so what was I saying here? mm, how can I do this question? I don't know. But I guess maybe some logic will come to me when I continue this. When I'm just going through examples, maybe something will pop up in my head. I'm hoping for that. So 3, 2, 1, and after that, what are the other ways? So when one was the root, when one is the root, is there any other cases? When one is the root, then it will just be 1. So since it will be in ascending order, so it will be one condition can be just right, because that will be one condition. One's right will be greater, this, like this way. And then another one can be one's right can be 3, and 3's left can be 2, right? This can also be one of the cases. If it is any greater number than 3 and 2, and this 3 to 1, this pair, so 1, 2, 3, 4, and will there be any other pairs? So for 1, these two are the thing conditions. For 2, this, for root of 2, this is only the 1. For 3, it can be this one as well, 3, and then left will be 1, and then right will be 2. Yeah, it was easy when n is equal to 3, but what if n is greater? How will I find? Is there any formula? I just need to return the number. I don't have to return all the different combinations, it is okay if I just return a number. How many will be formed? So acceptance rate is 61.8%. So how to do this then? What if like n is equal to 7? Then then what is the case? So if n is equal to 7, then it will be, it's not 7, but let's say if it is 5, then it will 1, 2, 3, 4, 5. Then what is the logic? So if the root is 1, then it will be left. What can be in the left? Nothing can be on the left, right? On the right, there can be 2. So if 2 is the root, then 2 is the root and there are 4 numbers. I guess it is kind of dynamic programming. So if 2 is the root, I can just find out what are the total solution if 2 is the root and number are just 4, right? And if I know that, then that is the solution for the root when root is 1 as well. And for 2, if I find for 2, right will always be 3. So for 2 also, to know how many roots are possible when 2, then I can just, yeah, I can, if I just know what is possible for 3, then it will be easy for to know what will be for 2. Yeah. And for 3, if I know what is possible for 4, then it will be easier, because one thing and then another thing can be for when left is 2, another one can be for when left is 2. Yeah, something like that, you know. So you see, I was saying that this is dynamic programs. Mathematical reduction, yeah, it can be, there can be mathematical reduction also. So given a sorted sequence 1 to construct a binary tree, yeah, thank god that. But I think one biggest takeaway is, whenever I see a problem, I always feel like, oh, this is so difficult, you know. So when I saw this, just by looking at this, I was like, how will I come to a solution? But when I kept looking at going through the examples, you know, just constructing trees, then it just came to me that, oh, this is a dynamic programming solution. So main idea is to just go through examples, create different examples, and just go through it, you know. So the solution automatically comes to the mind by doing that. Uh, that is the easiest way to come to the solution, just by going through the examples and running through examples, because the idea just comes, right? So here when I created this, I just knew that, oh, one's right will be 2, and if I knew what is possible for 2, then I knew I could know what is possible for 1, you know. So that, like that, the idea will automatically come up. Okay, so let's look at the solution, because I just have 7 minutes left. The problem can be solved in a dynamic programming way. Given a sorted sequence, tomorrow I have to wake up at 3 a.m. So I need to sleep very early. That is why I kept a timer. So okay, so given a sorted sequence 1 to n to construct the binary source tree out of the sequence. So sorry, I was distracted by what I'm going to do after waking up at 3 tomorrow. So let's look at this. Given a sorted sequence 1 to n to construct the binary source tree, we could enumerate number I in the sequence and use the number as the root. The subsequence 1 to I minus 1 on its left side would lay on the left branch of the root. Similarly, the right subsequence lay on the right branch of the root. Obviously, we then can construct the subtree from the subsequence recursively, right? That's what I was saying. So if it is 1, then right will be 2, right? And then if I know how many will be from for 2, then it will be easier for 1 as well. So if it is 3, then its left can be 2 and 1. So I can put 2 in the 2 first and then 1 again, you know. We can then construct the subtree from the subsequence recursively. Through the above approach, we could be assured that the BST can be construct all unique As you can see, the problem can be reduced into problems with smaller sizes. Instead of recursively solve the problems, we can store the solution of subproblems and reuse them later. Subproblems with smaller sizes, and we can store the subproblems and use them later, right? So two functions. The number of unique binary search tree for sequence of length and PIN is the number of unique binary search tree where number I is served as the root of binary search tree. So if I is served as the root of the binary search tree, then what is the number of the unique binary search tree? So suppose if 2 is served as the root of the binary search tree, then what is the number of unique binary search tree? That is the thing. Decide function we need in order to solve the problem. Total number of unique binary search tree is the sum of binary search tree FIN enumerating each number I as the root, right, from 1 to n. This is the GN. GN is the sum of FN. So particularly for the base cases, there is only one combination, G0, G1, 1. Yeah. So number of unique binary search tree for a sequence of length n is equal to, this is the sum, obviously, right? Like I said, like when 1 is the 1 is sorted as the root, when 2 is sorted as the root, when 3 is sorted as the root. That is the sum, obviously. So G0 will be equal to 1 and G1 will be equal to 1, right? Because if it is 0, then there will be just 1 if it will just be 1. So when we are when we are looping it, then Gi will be equal to J minus 1 plus multiplied by so this is the generalized formula. Gn will be equal to, from 1 to n, Gi minus 1 multiplied by Gn minus 1. So yeah, after this it is just simple, this one only. Yeah, this was actually not a medium question. That was that was what I was saying. It is hard. It was hard for me too. That's how most problems should be. If it takes 40 minutes to implement, 10 minutes to figure out, then you are typing with one finger. Okay, everyone. If anyone is watching, thank you so much, and bye. I mean, I know that I have not been solving questions properly these days. I just set a timer for 20 minutes and that's it. But I will try to actually code and submit successfully from next time, okay? And for that, I will have to start doing LeetCode problems early in day, because I always push doing LeetCode problems until the end of the day. So that is always keeping me from reaching the finish line, for LeetCode. So I'll try to just solve LeetCode problems early so that I have enough time to submit the problem successfully.